For kilometers below the surface of the Amazon rainforest, something is moving. It has no sunlight, no fish, no oxygen, and it has been flowing silently beneath one of the world's greatest rivers for longer than anyone imagined. Scientists didn't even know it existed until they started drilling in completely the wrong place. This isn't a legend. It isn't a theory. It's a verified geological discovery, confirmed by Brazil's National Observatory, published in peer-reviewed science, and it has already rewritten what geologists thought they understood about rivers on this planet. The name of this hidden river is the Hamza, and it raises a question that has quietly unsettled researchers ever since. If something this vast was flowing directly beneath the world's most studied river system, for all of recorded human history, what exactly do we think we know about this planet? If you enjoy real scientific mysteries backed by verified evidence, subscribe, because the deeper this discovery goes, the stranger it becomes. The Amazon River is not simply large. It's so dominant that scientists believe it defined everything about its basin. Every tributary mapped, every sediment layer measured, every water cycle accounted for. They thought the Amazon had no more secrets left to give. That confidence is what made the discovery so disorienting. Then a geophysicist named Elizabeth Tavares Pimentel began examining data from something completely unexpected: oil exploration wells. And what she found in those wells shouldn't have been possible. In the 1970s, oil companies drilled a series of deep wells into the Amazon basin, searching for petroleum reserves. They found none. The wells were considered failures. Their temperature data sat in storage for decades, largely unexamined, largely forgotten. Pimentel and her team at Brazil's National Observatory decided to revisit those old records. What they were looking for was geothermal heat, because the way heat moves through rock can reveal an enormous amount about what is flowing through it. Cold water absorbs heat. Warm water releases it. Moving water leaves a thermal fingerprint in the surrounding stone. And the fingerprints Pimentel's team found were enormous. The data from those abandoned wells revealed something nobody expected. Running almost perfectly beneath the Amazon River, at depths ranging from 1 to 4 kilometers, there was evidence of a massive, slow-moving flow of water. Not just groundwater, not just moisture trapped in porous rock, something that behaved like a river. The scientific team named it the Hamza River, in honor of Valia Manithal Hamza, the geophysicist who had first noticed unusual thermal signatures in the region decades earlier, but never had enough data to be certain. The Hamza is approximately 6,000 kilometers long. That makes it roughly the same length as the Amazon itself. But the similarities between the two rivers end almost immediately. The Amazon moves fast. Its average current ranges from 1.5 to 3 kilometers per hour in the main channel. During flood season, it pushes even faster. It's a dynamic, powerful, turbulent system. The Hamza moves at a rate that defies any intuitive definition of the word river. Scientists estimate its speed at somewhere between 1 millimeter per hour and 1 millimeter per day. Not per second, per hour, per day. So why does water move that slowly? The answer forces a completely different way of thinking about what a river even is. The Hamza doesn't flow through open space. It moves through solid rock, displaced grain by grain through microscopic pores in ancient sediment. And yet across those 6,000 kilometers, it is moving, continuously, directionally, toward the Atlantic. Something is pushing it, and that something has been doing so for longer than our species has existed. The rock beneath the Amazon isn't random. It's stacked, layer upon layer of ancient sedimentary material laid down over hundreds of millions of years. Within those layers, certain bands of rock are porous enough to hold water, while others are dense enough to trap it. What researchers realized is that those porous bands form a pathway, a continuous, continental scale corridor running west to east, tilted by forces that operated long before a single tree existed in the Amazon rainforest. The Hamza doesn't flow despite the geology. It flows because of it. And the force that created that geometry is the same force that built the Andes Mountains. But what researchers discovered next surprised even the most skeptical geologists on the team. When Pimentel's team analyzed not just the temperature data, but also the salinity of water near the Hamza's projected discharge zone in the Atlantic, they found something that confirmed the system was real, and that it was genuinely connected to the ocean. The deep Atlantic floor near the mouth of the Amazon shows evidence of fresh water seeping up through the sediment, arriving from a source beneath the continent, moving through channels no human being has ever seen. The Hamza isn't just theoretical. It has a detectable output, and that raised the next question immediately. How much water is actually moving through this system? The Hamza River is estimated to be between 200 and 400 kilometers wide at its widest point. That's not a typo. For comparison, the Amazon at its widest spans roughly 48 kilometers during flood season. The Hamza is potentially 8 times as wide. 1% of the Amazon's discharge sounds like a rounding error. It isn't. Applied to the Amazon's staggering volume, that figure represents more fresh water than most of the world's major rivers carry in their entirety. And it's arriving at the bottom of the Atlantic Ocean, cold, mineral-laden, chemically unlike anything that flows from the Amazon's surface mouth. Which raises a question scientists weren't prepared for. What has that water been doing to the deep ocean floor? All this time, the deep seafloor near the Amazon's mouth is one of the most biologically productive marine zones on Earth. It's been studied for decades. But what hasn't been studied is what happens when deep subsurface freshwater, chemically distinct from surface river water, mixes with the deep saline Atlantic floor. Subsurface water that has traveled through kilometers of sedimentary rock carries a different mineral load, a different temperature profile, different dissolved gases. The preliminary data didn't close that question. It widened it. Researchers working independently in multiple countries reached the same uncomfortable conclusion. The Hamza may be influencing the chemistry of the deep Atlantic seafloor in ways that have been misattributed to other sources for decades. Scientists had a word for underground rivers, but the Hamza didn't fit it. Known subterranean rivers flow through open passages carved by water, eroding limestone over thousands of years. You can enter them, so we can navigate by boat. The Hamza offers none of that. It moves through rock with no open channel, no cave, no cavity a human being could ever reach. It isn't a river hiding in darkness. It's a river hidden inside the planet itself. And that distinction is what makes its scale almost impossible to explain. What the Hamza forces scientists to confront isn't a small knowledge gap. It's a continental one. The current models of hydrology, the frameworks researchers use to understand how water moves across this planet, don't account for slow, deep, directional systems operating at this scale. Which means every water budget ever calculated for the Amazon basin, every projection about drought resilience, every model of how the forest survives, was built without knowing this river existed beneath it. But the evidence pointed somewhere no one expected. To understand why the Hamza exists, you have to go back roughly 10 to 25 million years. That's when the Andes Mountains began their dramatic rise along the western edge of South America. As the Andes pushed skyward, they reshaped the drainage patterns of the entire continent. Rivers that may have once flowed westward toward the Pacific were blocked, forced to turn east. And in doing so, they carved the Amazon basin as we know it today. But water doesn't only move on the surface. Underground, the story of that tectonic shift is preserved in the geometry of sedimentary layers that were tilted, compressed, and arranged by the same forces that raised the mountains. The Hamza flows through those layers along a path shaped millions of years ago by the birth of the Andes themselves. The river beneath the Amazon is, in a profound sense, a memory of a tectonic event that ended tens of millions of years ago. This geological perspective opened a question that researchers weren't initially prepared to ask. If the Hamza's existence is tied to the deep structural history of South America, could similar systems exist beneath other major river basins on Earth? That question is not rhetorical. It is actively being researched. Following the publication of the Hamza findings, geologists in multiple countries began revisiting old borehole data from other major sedimentary basins. The Congo Basin in Africa, the Ganges Plain in South Asia, the Siberian Plain in Russia. Thermal anomalies consistent with deep directional water flow appeared in records that had never been analyzed with the Hamza in mind. Not confirmed yet, not published as rivers, but present enough that researchers reached the same uncomfortable conclusion independently. The Hamza may not be the exception, it may be the template, and if it is, a significant proportion of Earth's freshwater budget may be moving through the planet's crust in ways that no existing model fully accounts for. Every hydrological framework ever built, every calculation of how water enters the ground, moves through it, and returns to the ocean, may be missing an entire category of system. Current hydrological models account for surface runoff, evaporation, transpiration, shallow groundwater. They don't account for slow, deep, directional continental systems, which means every water budget ever calculated for the Amazon was built without knowing this river existed beneath it. That's not a footnote. That's a foundational gap. Deforestation doesn't just remove trees. It removes the mechanism by which the Amazon recycles its own water. And if the surface cycle breaks down, less rain, less soil saturation, less percolation downward, the recharge rate of the Hamza could change in ways no existing model has ever tried to calculate. Scientists don't know if the Hamza is sensitive to what happens above it. They don't know because nobody thought to ask the question until now. That gap in knowledge may be the most consequential thing about this entire discovery. Elizabeth Pimentel and her team have been clear about one thing. The Hamza is a starting point, not a conclusion. What they demonstrated is that something vast is moving through the deep rock beneath the Amazon. What it does, how it connects to the surface, how sensitive it is to change. Those are questions that will take years, possibly decades, to answer. No camera has ever seen the Hamza's water. No instrument has been lowered into it. Every measurement, every estimate, every boundary drawn on a map of this river exists only in inference, in heat signatures, in isotope ratios, in the pressure of freshwater pushing up through Atlantic seafloor sediment miles from any known source. This is a river confirmed by its fingerprints alone, and scientists are only beginning to understand how large those fingerprints actually are. In 2024, a separate team of Brazilian and international hydrologists announced a renewed research initiative. New monitoring wells, designed specifically to gather thermal and chemical data from the Hamza system at far higher resolution than the original oil exploration wells ever provided. The goal is to build a three-dimensional model of the system, to estimate its true volume and flow rate, and to begin investigating how the deep subsurface interacts with surface hydrology under different rainfall conditions. The research is ongoing, but what the team has already confirmed is striking. The thermal signatures in the new monitoring data are consistent with the original discovery. The river beneath the river is real. It's present, and it's larger and more structurally complex than the initial findings suggested. In some sections of the Hamza system, researchers found evidence of not one, but multiple distinct flow horizons, separated by layers of impermeable clay and mudstone, stacked vertically through the sedimentary column. This means the Hamza may not be a single underground river at all. It may be a series of stacked subsurface channels, each flowing at different depths, different speeds, and carrying water of completely different ages. Water age is one of the most fascinating and least discussed aspects of deep groundwater systems. Scientists can determine how long water has been underground by measuring isotopic signatures. Water molecules contain atoms of hydrogen and oxygen, and naturally occurring variants of those atoms, called isotopes, are locked into water at the moment it enters the ground. As the water moves deeper and loses contact with the atmosphere, that isotopic signature becomes a kind of clock. The isotopic data from the Hamza's western extent, near where Andean rainfall first enters the system, carries a signature unlike anything near the surface. Its hydrogen ratios, its oxygen balance, its dissolved mineral load all point to a recharge environment that no longer exists. The rainfall patterns that fed this system, the climate that produced this water, they belong to a world that ended thousands of years before the first human civilization built its first city. The Hamza isn't just old. It's a sample of a planet we have never seen. That number, 300,000 years, changes everything. It means the Hamza isn't a resource. It's a record, a continuous, pressurized archive of precipitation events stretching back through ice ages, through warm periods, through climatic shifts that reshaped every coastline on Earth. And it's sitting undisturbed, 4 kilometers beneath one of the most rapidly deforested regions on the planet. What happens to an archive when the conditions above it change faster than at any point in the last 10,000 years? That isn't a rhetorical question. It's the one researchers are now racing to answer. Here's what we know with certainty. There's a real, confirmed, continental-scale, subsurface water system running beneath the Amazon River. Approximately 6,000 kilometers long, moving at extraordinary slowness through porous sedimentary rock, discharging fresh water into the deep Atlantic. Named the Hamza, after the scientist who first suspected its existence, and confirmed only in 2011 by a team working from oil exploration data collected decades earlier for entirely different reasons. Here's what we don't know: how the Hamza interacts with the surface water cycle above it, how sensitive it is to the dramatic environmental changes now underway across the Amazon, whether similar systems exist beneath other major river basins, how old its water truly is, and how many distinct flow layers it contains. Here's what researchers are beginning to suspect. The Hamza is not an exception. It may represent an entire category of large-scale subsurface systems existing beneath continental interiors worldwide, invisible to surface observation, operating on timescales that dwarf human civilization, carrying water whose origins lie in climates that no human being has ever experienced. And if that's true, then Earth's water cycle, the system we think we understand, the cycle of rain and rivers and oceans and clouds that has supported life on this planet for billions of years, is more complex, more layered, and more mysterious than our best current models suggest. The Amazon, runs above the surface. It's immense, it's biodiverse, and in many ways, it's still unknown. But 4 kilometers below it, there is another Amazon, colder, darker, slower, ancient beyond reckoning. And the deepest question we can ask isn't how it got there. It's this: if a river of this scale could hide beneath the world's most studied rainforest for all of recorded human history, how many more are hiding beneath everything else?